Hello, my name is Carlos Terán, and I'm a PhD student at the University of Puerto Rico, Mayagüez, and I'm member of the Laboratory for Applied Remote Sensing Images and Photonic. This work is called Hyperspectral and Multispectral Image Fusions using a Multi-Level Propagation Learning Network. Well, the outline of these presentations is as follows. I'm going to give a brief introduction of imaging fusions, the challenges and motivation of this work. Then I'm going to introduce our proposed approach that is called Multi-Level Propagation Learning Network. I'm going to present the result generated by our approach, and finally the conclusion. Well, data fusion technique is a hot topic in the area of remote sensing because the capability to obtain measurements from the same scene using different sensors that provide a variety of resolution domains. In particular, this work provides a new approach to fuse multispectral images that contains a high spatial resolution and low spectral resolutions with high spectral images that contains low spatial resolution and high spectral resolutions to obtain images with both domain in high resolution. This new approach generates new model for satellite imagery fusions called Multi-Level Propagation Learning Network, which is based on long-short-term memory architecture. This new approach provides a model that can be trained with variable path size and provide an intrinsic data augmentation, reducing the required number of training samples. Well, let's see the motivation and the challenge of this work. In order to provide a high accuracy in classification problems using hyperspectral images, it is mandatory to have a high quality image. There are sensors that can provide such images, but they are highly costly. As a consequence, we propose to fuse multispectral and hyperspectral images to obtain image with high spatial and high spectral resolution. Most of the models presented in the literature require a considerable amount of data for trainings, but usually this amount of data is limited. Consequently, we design a mechanisms to manage a scenario with low data training, which also provide an intrinsic data augmentations during the training stage. Well, now, in order to introduce our model, let's define a new concept that is sequence of images and introduce two parameters called padding factor and scalability number. A sequence of images is defined as the set of images which satisfy the following properties. The images are square and the images on the sequence are concentric each other. The padding factor parameter crop an image generating as sub-images, losing the provided quantity of pixels. Now, the scalability number sets the number of cropped images. In other words, it is the cardinal number of a sequence of images. This figure provides an example of a sequence of images. The figure A shows the set of images generated using the parameters scalability number equals to 9 and the padding factor equals to 1. The same way, the images B, C, and D provides a sample of sequence of images for difference value of the padding factor and the scalability number. Well, the multi-level propagation learning network is built using a layer of long-short-term memory, a fully connected layer, and a regression layer. This model is fit using the sequence of images which elements are arranged from the smallest images to the largest ones on the sequence. In this way, the network can propagate information learned from the small spatial area to the largest spatial area using the main characteristic of the long-short-term memory network. Well, in order to generate our results, we use two different datasets. The dataset used for our experiments and results were two. They are Enrique Reef hyperspectral images and Indian Pines hyperspectral image. The model were trained with two different percentages. in order to provide the performance of our model. And also, we use a different initial patch size to study the performance of the proposed model. The model we're training with two different percentage, as I mentioned, and in this, for the first set of data set, that is Indian pine, for Indian pine data set, we can see that using 80% of data for training and a patch size of 16 with a scalability number of 20 and padding factor of 1, and also using 20 bands, we got a better result. Even that, using a 40% of data for training, we obtain a similar results that using a 80% of data for training. For Enrique Reef dataset, using a patch size of 12 and a padding factor of 1 and scalability number 4, and using 16 bands, using 80% of data for training, we got the best results, even though using a 40% of the data for training and a patch size of 8 with a scalability number of 3 and padding factor 1, we got a similar result. Well, the proposed approach to generate images with high spatial and high spectral resolution images fusing multispectral and hyperspectral images provide outstanding results. Also, we introduced two new parameters that help to generate data augmentation in the training stage. We have shown that using less data for training, we are still having good results. Well, thank you for your attention.